Hey physics class, we're going to bring back Ohm's law in a way that's going to be integrated with solving circuits and finding their equivalent resistance. So we talked about Ohm's law just solving for current given a voltage and a resistance, and that's usually how a circuit shows up in a problem. So let's just start with a quick sample. Okay, so we've got a circuit here. Let's give ourselves a 5-volt battery, and since we're going to have a 5-volt battery, let's have a resistor that has nice easy resistance for the calculation. Oh, let's say 5 kiloohms. No need to make this tricky. Okay, so a 5-volt battery, 5 kiloohm resistor. Ohm's law says V equals IR, that the product of the current and the resistance is the voltage. Since we know what the voltage is 5. We know what the resistance is, it's 5,000. Then what we are left with is an unknown current. And you don't need to see this on a calculator, but I mean, I got the calculator, so why not use it? 5 divided by 5,000 is 0.001. That means that the current is 0.001 amps. Amps equals the current, and if you like, we could call that 1 milliamp. Anyway, that is Ohm's law as it applies to a resistor with a battery. Now let me redo this circuit, but make it just slightly different. So I've got a 5 kiloohm resistor. Now if I were to make a twin of this, oops, almost messed up the battery. Okay, and this time with our 5-volt battery, we have a 2 kiloohm resistor in series with a 3 kiloohm resistor. What now? Well, if you know how to solve a circuit like this, then you'd know that a 2 and 3 kiloohm resistor in series adds up to a 5. So these two circuits are practically the same circuit. They have the same resistance. However, when it comes to those two resistors, they have current running through each of them individually. Is it the same? They have a voltage that is going across them. Is that the same? Okay, so in the case of something like this, it's actually helpful if we can set things up a bit more clearly. So I'm going to reproduce that circuit on a fresh sheet, and I'm going to set up a table that's going to be a nice solving mechanism for us to use. So we had a 5-volt battery, 2 resistors, oops, there we go, 2 resistors in series. It was 2,000 and 3,000. Okay, I'm going to name these because, you know, I don't want to just keep referring to it as the 2001 and the 3001. Let's call this resistor 1 and resistor 2. I named them 1 and 2 in that order because, well, I'm picturing the electricity going clockwise, so it hits that one first. So hopefully that doesn't confuse you if you're used to reading from left to right. Okay, so I've got 2 resistors, and here is a table I'm going to set up. I've got resistor 1, there we go, and resistor 2. Now, resistor 1 and resistor 2 each have a resistance. That's not hard. But what's tricky is they also both have a current running through them, and they also have a voltage across them. I will explain all of those as we get to them, but let's just start with the easy one. We have their resistances. So the resistance of resistor 1 is 2,000. 2,000 ohms. And the resistance of resistor 2 is 3,000. Okay, so that's not hard. What do we do about the current? Well, in order to find the current that is going through those, we would need to know the current going through the entire circuit. We've actually already solved that, because remember what I said, that circuit is, from Ohm's law's point of view, indistinguishable from this circuit. This circuit had 1 milliamp of current, so this one does too. The question is the same current going through both resistors? Well, the answer to that is yes, because current is just the amount of electricity flow. Since there's only one path, the amount of electricity that flows through the first resistor must also flow through the second resistor. Pardon my imprecision. When I say the amount of electricity that flows, I mean the number of electrons that pass through. So the current must be the same as it was before. 1 milliamp. And it's worth noting at this point that the current for two resistors in series must be the same. In fact, I'm going to write that down. Current for resistors in series must be the same. What about the voltage, though? So it turns out the voltage is what is going to be different. So we can look at this actually two different ways. We know what the current is through resistor 1. We also know what the resistance is through resistor 1. That's actually two of the terms in Ohm's law. So if we were to do V equals IR for the entire circuit, we would be doing 5 for V, 5,000 for R, because that's the sum of those two resistors, and then we calculate I to be, 1/1000th of an amp. But what if we did it just for resistor 1? What if I did, here, I'll do a different color. What if I did this? That would be that the current through resistor 1 times the resistance of resistor 1 equals the voltage of resistor 1. Now, resistors don't have voltages, as in they're not sources of voltage. So what does it mean if there is a voltage associated with a particular resistor? Well, think about what voltage is. Voltage is an electrical energy difference, as in there is a surplus of electrons on one side of this battery and a deficit of electrons on the other. Electrons have charge energy, which means if they're collected in one place, that's a concentration of energy. The energy wants to spread out. And the fact that there is a different concentration on both sides of the battery means there is an energy difference. Well, that energy difference is going to be spent as the energy spreads out. It costs the battery to pass electricity through this resistor, which means on the other side of the resistor, that energy has gone down some. Okay, so let's put the numbers in. The current through resistor 1 is 0.001 amps. The resistance of resistor 1 is 2000. So now we can find the voltage across resistor 1. And just clear this. So 0.001, that's the current, times 2000, that's the resistance, 2 volts. Well, let me go ahead and write that in. What does that mean? It means that 2 out of the 5 volts got spent on crossing resistor 1. After doing the work of passing through resistor 1, the 5 volts has been reduced to 3 because 2 of them are gone. Okay, well, let's go ahead and do the same thing for resistor 2. It's almost not worth writing out if you've been following the math on it, because if we've got V equals IR with 1s, I can do the same thing. Voltage across resistor 2 equals the current through resistor 2 times the resistance of resistor 2. That would be the same current, 0.001, times that resistance, which is 3000. And I think you can already tell where the math is going to go on this. 0.001 times 3000. That is going to be 3. Okay. So, what this means is, if you want to know what is the voltage in the circuit, there's a couple different ways you could answer that question. One way is you could just look at the battery and say there's a 5-volt battery on the circuit, there's 5 volts. Okay, that's fair. But what about in the middle of the circuit? So remember, we're talking about an energy difference that is based on the concentration of electrons, or the force that is driving electrons through the wire, let's say. So if you wanted to kind of poke your head in that wire and, you know, kind of like, how hard are the electrons blowing today? You can't do it just like this. Let's say you give the electrons a wire to go through, and you want to see how hard they push in. If this wire is a dead end, it's not actually going to let any electrons through. You will feel nothing. You actually need 2 measurements. So let me just draw a little thing on here. Try not to mess up the circuit, but just bear with me. If I were to have a device, if I were to have a device which could measure the voltage, it would have to stick in at 2 places. Basically, it is a little side channel for the electrons to pass through, and it's going to measure how hard the electrons are pushing through. And you'll notice that there is a little gap there. So, if you were to measure right here, you'd actually find that the voltage was 0. Why is it 0 right there? Well, it's because there's no energy spent going from here to here. Okay, think about this from a elevation point of view. So I'm going to take this circuit again. But this time, I'm going to draw it like it was elevation. Okay? Remember, there was a 5-volt battery, which means that the energy difference between the beginning and the end was 5. I'm going to draw another scenario where the energy difference between the beginning and the end was 5. So here's 1, 2, 3, 4, 5. Let's just say this is like 5 levels, like, 5 steps on a staircase or 5 floors on a building. Just call them 5 levels. And this would be the start, of course, and the end is on the ground. Okay, how do you get from the start to the end? Let's just say you You just start up here and then just straight down to the end. So from a circuit point of view, that's a short circuit. Just nothing at all between the start and the end. Just straight dump the energy out. That's it's not interesting. It's not really worth considering. We're trying to do circuits. This circuit has two steps. The first step is small, the second step is large. It actually kind of looks like this. All right, what are we looking at here? So this is a drop of 2. That's representing this resistor. The other resistor is represented by this. Okay, so as I almost feel like I should draw it again in this space so I don't have to keep going back and forth. So here's our beginning, our start. Here's our end. Instead of going down a slope, we're going to go around. But, you know, you've got an imagination. You can kind of do that work in your head. So as you move around this wire, that's kind of like moving across that top level. You're moving, yeah, but not towards the end, right? There's no work done to just slide around on the top. You're not falling. Remember, if the energy we have here is from the height, if you're not changing your height, then you're not changing your energy. So as you move around this wire, if it's not costing you any work, then you're not really going down in voltage. Everything here might as well be the post of the battery itself. Okay, so let's actually stick a resistor on there. Okay, that actually changes the amount of energy because it costs energy to cross it. This actually changes the amount of energy. Afterwards, you're only down to 3 because 2 of them are gone. That resistor is equivalent to that step. And the height of that step corresponds to the resistance of this resistor, because this was not specifically 2, but 2 out of the total. Okay? It's going to cut 40% of the voltage of the battery. Okay? So if this went up to 50, this would have been 20. Okay, the other resistor, see, as you move towards that resistor, yeah, you're moving, right? But you're not actually changing the amount of energy. Second resistor, last step. And what that means is everything past this, it's all on the bottom. You might as well be on the battery itself. The length and the orientation of the wires shouldn't matter. The point is just what is connected to what. Okay. So, if we've got this kind of visualization, then we can think of resistors as dropping voltage. We could say that voltage drops across resistors. So let me write this down. I'm going to say voltage drops across, this is the terminology, across resistors. I'm just calling them R's so it can fit. Voltage drops across resistors, and it's going to be proportional to whatever fraction of the total resistance that resistor is. So proportional to that resistor's fraction of the total. Okay? So if you've got 2 resistors that are both equal, they will each take half the voltage. If you've got 3 resistors that are all equal, they'll each take 1/3 of the voltage. In fact, let's do one more so that it's not quite so obvious, because I made the numbers be easy for math, but sometimes that actually ends up being misleading, because when you see a 5, you're not sure where the 5 came from. So one more example, and then I will do something else. let's have a more common battery. Let's actually have a 9-volt battery. Okay, 9-volt battery. 9 volts. And let's have 3 resistors. I'm going to not go with thousands. So this could be 10 ohms. Let's see, this one can be 20 ohms. And this one can be 30 ohms. There we go. Okay, so a 9-volt battery, it's hooked up to a circuit that has 3 resistors, and let's go ahead and label these. I'm going to make a table like I did for the other one. This can be R1. I'll use that color for R1. This can be R2. I will use that color for R2. And this can be R3. I will use that color for R3. Let's see how much time I spend capping and uncapping markers. So if I've got those 3 resistors, then I can start to make this table. R1, R2, R3, and let me set up the rest of it. Hold on. Okay, so resistance is easy. Oh, hold on. Okay. Current, slightly more complicated. Voltage, slightly more complicated. So let's just complete this table. Hold on. Yeah, sound effects for markers. That's just the height of professionalism. All right, so this is such an ugly table. I'm sorry, table. I didn't mean to say that. Beautiful. Okay, so the resistance of resistor 1 is 10. That one's not controversial or difficult. The resistance of resistor 2 is 20. Again, not difficult. The resistance of resistor 3 is 30. Not difficult. So what's the resistance of the entire circuit? Well, they're all in series, so it's 10 plus 20 plus 30. That would be 60. The total resistance is 60 ohms. Well, you know what that means? It means that resistor 1 actually is 1/6 of the resistance. It's 16.7% of the resistance. 20, well, that would be 1/3 of the resistance. 33.3% of the, oh, I'm using the wrong color. Sorry. All right, so resistor 2 itself has 33.3% of the resistance in it. And this last one, R3, it's 30. The total is 60. This is actually 50% of the resistance right there. Okay, since we've got 1/6 of the resistance right here, it means that that battery spends 1/6 of its energy crossing this resistor. Since this is 1/3 of the resistance, the battery spends 1/3 of its energy crossing this resistor. Since this resistor has half of the resistance, the battery spends half of its energy crossing this resistor, which means that the voltage across resistor 1 should be 1/6 of 9. Let's just do the math on that real quick. Clear that. All right. So 9 divided by 6 is 1.5. We lose 1.5 volts across resistor 1, which means by the time we get to resistor 2, we are down to only 7.5 volts. Okay, so let's have a look now. Resistor 2 has 33.3% of the resistance in the circuit. It's using a third of the battery's energy to cross it. This one I'm not going to use a calculator for because it's just too easy. A third of 9 is 3 volts. Something worth noting, you know how 20 is twice of 10? Resistor 2 has a resistance double of resistor 1. Well, it also has twice the voltage. Remember, it's proportional. And the last one, half of this would be 4 1/2.